everybody. My name is Hunter Wack, Business Development Manager here at Rayco Rents. Thank you all for taking time out of your busy schedules to join us for this webinar. Our presenter today is Dusty Ott with SKC. He's going to give us an in-depth look at the advanced noise measurement strategy, specifically with the SKC NoiseChek dosimeters. Some topics he will cover today include generating reports, how to make informed decisions using sampling data, advanced data track software features, setup and data interpretation, lesser known abilities that streamline noise analysis, key parameters, highlighting differences and understanding the right situation for when to use key parameters such as L average, LEQ, L peak versus L max, etc. Dusty is a Swiss Army knife at SKC, focusing on occupational health and safety instruments, and has been a part of their team for a little over a year. Dusty has been a great resource for Rayco Rents, providing technical insight to all of SKC's products. Whether it was at a conference or an AIHA event, it's always nice to have a friendly, reliable face that understands the equipment at a deep level, such as Dusty and his colleagues at SKC. Since we have a large number of attendees, everyone will be muted. We do have a chat box that you can use to ask any questions or leave comments. We will try to answer all questions at the end of the presentation if we have enough time. About 1 or 2 hours after the webinar, you'll receive a certificate of attendance along with a recording of the webinar. If you don't receive this, feel free to send us an email and we'll send that to you. The webinar will also be posted on our website for you to view at any time. I'm going to turn the mic over to Dusty and let him take the lead. Welcome, Dusty.
Thank you, Hunter. Just making sure you can hear me before we get into it.
Good to go, sir.
Awesome. Well, thank you again for having me on here. And like Hunter said, my name is Dusty Ott. I'm the corporate IH over at SKC. And it's amazing that I've already been there almost or a little over a year now. Time flies when you're having fun. So like Hunter said, we are going to talk a lot about the noise dosimeter today, field applications, some personal stories and lessons learned along the way. And then I'd like to spend a decent amount of time toward the end going through the software, how I would use it, and some of the things that you can do that can make your life a whole lot easier as an industrial hygienist. And so to start things off, we all know that accurate noise measurements are absolutely crucial in our job. And so today I want to give you some insights and guidance on how to do that to make the most of the time that you have in the field. We're going to look at and understand some concepts to ensure your accurate assessments, they are complying with MSHA or OSHA or the ACJH, depending on what your company falls under. And then ultimately, we're gonna utilize some modern dosimetry and software to rock your world, to make your life easier. So with that being said, we are going to clear up some common monitoring misconceptions. You heard Hunter in the intro kind of talk about TWA, L average, LEQ, L peak, max. There's a lot of these L words out there in the sound world that can be confusing. I'm hoping to help unconfuse that today. I've spent a lot of time over the last week trying to explain this to my kids so they understand it. So hopefully I've figured out a way to explain each one that makes sense through a webinar. So we've already talked about the rest. Let's just get right into it. So on a basic level, sound is pressure waves. There are pressure waves that are generated by vibrating objects, whether that's you hearing my voice right now going through my speaker through the internet, and then your speaker is vibrating and you are hearing, your ears and your brain are discerning the pressure waves into sound. And so the couple key things that are associated with this are the amplitude and the frequency. That's also known as how loud it is and the pitch. And so I really like this picture a lot because growing up, you always see like sound waves described or visualized as like sine waves just going through the air. And as a human, it's hard to like see a sine wave shooting off of something that's making noise. So this picture I really enjoyed because you're seeing the actual vibration of that wave in almost a cross-sectional view. So you can see that there's little compactions, little rarefactions, and that has to do with the frequency and how tall or big those waves are. That has to do with your amplitude. We'll talk a little bit more about amplitude and frequency later on and how that relates to decibels, pascals, and other things. But for now, I really enjoy this when you're trying to explain to somebody how sound works, and sine waves just aren't cutting it. As far as frequency, like we talked about, frequency is the number of waves per second measured in hertz. And in the human ear, our range of hearing is from about 20 hertz or 20 vibrations a second up to about 20,000 hertz or 20,000 hertz or 20,000 vibrations per second, which is incredible. But in our world that we live in communication and talk to each other, the most important, quote unquote, important frequencies are that 250 to 8,000 hertz range. And so we look at these two pictures and we see on the bottom, the picture is an A-weighted filter that is laid over most of our noise sampling. If we talk about C-weighted and Z-weighted, that's a little bit different. Right now, we're going to be talking primarily about the A-weighted filter that we use in our dosimeters and in our sound level meters. So if you look at this blue overlay that I just threw up there, you'll notice on the left picture on the A-weighted curve, that range between 1,000 and 10,000 hertz is almost exactly on the line of zero gain. And the reason that we use an A-weighted scale for the type of measurements that we do is because the A-weighted most closely associates with human hearing. Now, if you look at that upper right picture, this is an audiogram of somebody who has some pretty profound hearing loss. So that same range is overlaid on there, and you see that from about 1,000 to 8,000 is our stereotypical noise-induced hearing loss notch. Now, why that's important, it will be very apparent on the next slide when we talk about the frequency ranges that we are talking and communicating on a daily basis. And so if you look at this scale, the range from 85 to 300 hertz, this is fundamental speech. This is a little bit deeper end of the spectrum, especially for male voices. This is typically a range that is not as affected as much by noise-induced hearing loss that we find at work. The next area is the 300 to 3,000 range, and this is the core intelligibility, or all the consonants and the vowels. That's a huge portion of how we talk and communicate. And then that 3,000 to 8,000 hertz range, this is our sharpnesses. This is our S's, our T's, our F's, our TH's, our SH's, our sh's. And so kind of the running phrase I like to use when you're trying to talk to somebody about hearing loss and why it makes a big difference in their life, if they're wearing a watch and you say, "What time is it?" and they say, "Oh, it's a Rolex," they might have heard time, but they probably heard kind. And so in those, when you're experiencing hearing loss, K's and T's and other of those sharp consonants that are listed here, they kind of mimic each other and they blend together. And so I don't know if any of you have had grandparents or parents or yourself have a lot of hearing loss, but communicating becomes a lot more of a challenge. I know growing up, my grandpa worked as a mechanic in a truck yard, and trying to have conversations with him was always very challenging because I would have to speak very, very loud, very slow, and I was always mumbling to him no matter how much I enunciated. So as an industrial hygienist, like learning how to explain these things to people has been a huge part of my career, and being able to help them understand why it matters down the road if their hearing is damaged while they're at work. And so I would just encourage all of you listening today that to take the time and think of how you talk to employees about noise, whether that's noise training, noise awareness, whatever it might be. Find things and find ways that will be personal to them, that will help them understand why it's so important for them to keep their hearing. Like, what's the point of working your entire career, lose your hearing, and then suffer the rest of your life with having communications with your grandkids, your wife, your friends? Like, it just makes a lot of sense to take the time to help them understand. Even if they already have hearing loss, protecting what they have left is still super important for them, probably more important for them because they're already at such a disadvantage. So as far as sound pressure levels go, these next couple slides get kind of nerdy, like hang with me. Sound pressure, it's measured in pascals. And the way that this works is sound pressure is directly related to decibels on a logarithmic scale. And so you are converting sound pressure levels to decibels through this particular formula right here. So in short, the decibel is a logarithmic function of the ratio of the sound pressure and the reference pressure. And what the reference pressure means is what the threshold of human hearing is. Now on that first bullet, you'll see the human hearing threshold is 0 dB or 0.00002 pascals. So as you go down this slide, what we find out if you throw some numbers in this equation, every 6 decibels of noise that's increased, it is perceived, it is twice as loud. So a sound that is 91 decibels has twice the pressure as a sound that is 85 decibels. Now that last bullet point is what humans perceive as being twice as loud. And so our perception is that every 10 decibels we increase is twice as loud. In reality, 10 decibels, a 10 decibel increase is actually 3.4 times as loud. So if you focus on this little Excel graph that I've made on the right side, you'll notice as we go down the scale, it kind of gives you an idea of how much pressure has changed over the course of the sound wave. So we look at 85 decibels right here. Like I said before, when you go over to 85, go over to this little 0 part, go down to 91, and we see that 91 has twice the pressure as 85. If you want to go all the way down the scale, a sound that is 145 decibels is 1,024 times the pressure that a sound that 85 decibels is. Okay, again, this is a little bit nerdy, but it's kind of fun as well to understand and learn. Moving on, the next slide is about sound intensity. Now, intensity is actually how much sound energy is being transmitted through the air into your eardrum and into your ear. In short, with intensity, every 3 decibels that the sound increases, it doubles the intensity. So it's twice as much as the pressure. And I'll tie these together in the next slides to where they make a little bit more sense. So for example, you take a sound that's 85 decibels, you compare that to a sound that's 109 decibels, it's 256 times more energy or 256 times more intense. And so to tie those two together, we have sound pressure and sound intensity. So if you think of it as a concert, is the sound pressure is how loud the music feels where you are in the crowd. Like you can feel the bass, you can hear the guitarist, you can experience that sound, you feel that in your chest. Whereas the sound intensity is how much actual energy is making it into your ear. It's kind of a fun way to think about it. I got a big old spreadsheet that we could go through if you wanted to see how these all relate, but I wanted to help understand, especially from these graphs right here, that when you're talking about reducing noise exposure at work, that people are like, oh, you only reduced it 6 decibels. Well, yeah, but reducing it 6 decibels, that's 4 times less than it was before. Like that's a huge amount of energy that you have taken out of that situation. One of the examples that I have from when I was at Hill Air Force Base is we had a blast booth that was meant for blasting dried glue off of the F-16 wings. Inside of that booth was 115, 116 decibels, and we were butting up against the OSHA limits for time limits, even with the hearing protection that they were using. And so we're saying, you know, if you can just, even if you can reduce this by 3 decibels, we can work with that. We can get some additional time, we can do other things. And they were like, only 3 decibels, that's not very much at all. But helping them understand that every 3 decibels that you reduce, you are reducing the intensity by 2 times. So basically 50% of the intensity, which is a massive reduction. So there's that. So moving on to a little bit of our LEQ, L average, and time weighted average. This is just a summary of each of these on this page. As we move over the next few slides, I'm going to go into more detail of each one. This is just kind of a summary slide to get after it. And so when we're talking about our time weighted average, this is, you have to always remember, this is a fixed time period. This is the level, this is either the level that you were experienced at exactly 8 hours, or it's the equivalent level that you would experience if your shift is longer than 8 hours. Every job that I've had, other than working at SKC, we've worked either 10 or 12-hour shifts. So all of our time weighted averages were a 10 or a 12-hour shift that was squished down into an 8-hour equivalent. So what this does is it represents the constant sound level lasting 8 hours that would result in the same sound energy as the noise that was sampled. It doesn't matter if it was 8 hours, 9 hours, 10 hours, 12 hours, it would be the same amount of sound energy averaged over that time. Now, if you look at that bottom bullet with measurement times, when we're talking about time weighted averages and L averages, there is a definite correlation between the two. And we're going to go into L average more on the next slide, but kind of to prepare you for that, if we have a measurement and we look at our software, we look at our graphs, and we see that we have a measurement that was less than 8 hours, our time weighted average is always going to be less than the L average. Only at 8 hours and only at 8 hours is our time weighted average exactly the same as the L average. Now, for the majority of us on the call that have tasks and jobs that are longer than 8-hour shifts, this is where most of us are going to fall. And at 8 hours, the time weighted average is always going to be higher than the L average. So what you're doing is you're squishing a 12-hour reading into 8 hours. And so I found this awesome picture of a cat that's trying to squish itself into a really small container. And that's kind of what we're doing when we're looking at the time weighted average of something that's longer than 8 hours. Is you're taking the sound, all of that information, all of the exposure that happened over 12 hours, and you're squishing it and you're compacting it into the size of something that was supposed to be 8 hours. And so even if you had the same energy the entire day, let's say you're exposed to 90 decibels constant sound the entire day for 8 hours, that would be 90 dB. That makes sense. If we sample for 9, 10, 11, 12, even if that 90 dB continued into the hours beyond our 8-hour shift, that additional noise is then squished into that first part of the shift. And so our time weighted average would be somewhere in the 90, maybe 91, 92, 93 decibel range because of that squishing effect of the noise. So when we're talking about L averages, it is the average sound level measured over the runtime of the measurement. This is not constricted by the length of your shift. This is the actual average of the full time being sampled. You're assuming it has a 5 decibel exchange as well as a threshold that you would use under OSHA or MSHA, which is 90 decibels. So it's measuring the same way that the time weighted averages. It is just not restrained by 8 hours. So moving on to the last one, which is our LEQ. The LEQ is the true equivalent or the actual sound level measured over the runtime. So we're going to get into more of this in our software discussion, but most software, the dosimeters can run for log either a 1 second average or a 1 minute average. And if you're logging a 1 minute average, what this is going to do is taking a minute and it's averaging it over that entire minute, and that's the plot that it's putting onto the graph. That's the data that it's using. And so by looking at the entire shift, there's no thresholds, there's no time limits. This is your actual average sound level over the entire shift, assuming that you have an exchange rate of 3 decibels and no threshold at all. So we will look at that a little bit later on when we talk about the software and what that kind of looks like. So as far as our impulse noise, we are looking at LPK. That is the highest unweighted fast response sound level measurement during that sample period. That is, it's measured differently than the rest of the information on our dosimeter. And what I mean by that is, back in the day, when I was first in my internship at the mines, I'd look at my noise report and I see LPK of 135 decibels. I'm like, holy cow, what is 135 decibels when I was just, walking around outside? Like, that is insane. That comes back to the misconception people have with LPK and Lmax. So just understand from a regulatory point of view that LPK is measured differently than the rest of the data that's on the dosimeter. It uses a different weighting, it uses a different response, and it has a different exposure limit, which is, the OSHA limit is 140 decibels. So we're going to contrast that with max, and our Lmax is the highest unweighted, or the highest weighted slow during the sample period. And so it's almost like the inverse of what the LPK was. So the Lmax, it pertains to the signal limit, it pertains to how loud of a sound there was during that shift. And so the OSHA and the MSHA limit are 115 decibels for an Lmax, meaning that you should not be exposed to anything above 115 decibels. And again, we'll be able to show this really well in the software toward the end of the presentation. So that's where the main difference is between Lmax and LPK. And from an industrial hygiene point of view, I really enjoy using Lmax on the graphs, and I'll show you a little bit about that more later on. So as far as dose, criterion level, threshold, exchange rates, I think these are all pretty understood in our field. I'm not going to spend a ton of time on them. Basically, our criterion level, that's 90 decibels for OSHA and MSHA, 85 for ACGIH. For a threshold, this is a level that the noise is not going to be added to our measurement unless it's that or over. So when we're talking about hearing conservation, that has a threshold of 80 decibels. So anything under 80, it's not picking up. Same thing for OSHA or MSHA from a regulatory point of view. They are set at 90 decibels threshold. So anything under 90 decibel threshold, there will be no addition to the time weighted average or the L average. From the exchange rate, we're looking at an exchange rate or a halving rate of 5 dB for OSHA and MSHA, as well as 3 decibels for the ACGIH. So as far as regulatory goes, we've already kind of talked about 90 decibels for OSHA and MSHA. Once you bump into that hearing conservation, and we'll get a little bit more into that as well, is you have to do noise monitoring, you have to do audiometric testing, you have to have hearing protectors, you have to train your people, and you have to keep a lot of records. So the action level for what we're looking at is a 50% action level, or 85 decibels, with a 5 decibel exchange rate when we're talking about OSHA and MSHA. And the one thing that's really interesting that I was very keen to at the mines is MSHA does not allow for age correction. So we would have a lot more standard threshold shifts as the miners got older, because we could not adjust for their age. Right, wrong, or indifferent, that's the way that it was written into the regulation, and so that's what we have to deal with. So from a hearing conservation point of view, as it's written in the laws, we have to enroll in a hearing conservation program when our action level is greater than or equal to 85 decibels time weighted average. Same thing with your dose. If it's above 50%, you're in that. And when you set up your dosimeter for the hearing conservation part of this, you have to make sure that you have a threshold of 80 and not 90. That's something that people can confuse and mess up, but make sure to have a threshold of 80 decibels for this. So because we all use type 2 dosimeters and type 2 sound level meters, that has a plus or minus 2 decibel range. So the conversation is, well, do I enter somebody into hearing conservation when they're at 85? Do I wait till it's 87? Do I do it before at 83? So based on the level of, not how much they care about their employees, but just based on their level of risk that they're willing to take, is conservative companies will enroll people into hearing conservation as low as 83 decibels because of that plus or minus 2. And those that are acceptable, they're fine with accepting additional risk. They won't enroll their people until they reach that 87 decibel threshold because of that plus or minus 2 decibel range on our dosimeter. So to kind of show it again right here, so with the corrective action level, you are bumping your level all the way to 87, and you're changing it from 50% up to 66%. Now, the other reason that somebody would need to be enrolled in a hearing conservation program, other than the readings that they've had on their dosimeter, is that they've had an actual standard threshold shift, which is a loss of 10 dB across the 2, 3, 4,000 range compared to their baseline. And so the kind of takeaway from this area is whether you choose to use 83, whether you choose to use 87, it depends on the level of risk that you want to accept moving forward with this individual in your company. So this is a graph that this is a table that we're gonna look at a little bit later on. But this was a really interesting and really fun measurement to look at, because if you look at it, like he is right there. Like he's just barely over where it's legally required to be in hearing conservation by 0.3%. So when I was looking through some of the examples that I have in the software, like this one is like, it's perfect. Like he is in hearing conservation by just the skin of his teeth. So we're going to look at this example again in the software, and based on a couple changes that we could probably make, we might be able to get this guy back out of hearing conservation, which is kind of fun to do in the software. So stay tuned for that. So moving on from hearing conservation, moving into some actual survey in the field kind of experiences, kind of things to remember, is always remember to check your batteries, whether that's if you're using dosimeters that are rechargeable, or you're using dosimeters that use AA batteries like the old 3M ones that we used to use in the mines. Like we would have to change the batteries every single time we sampled, or we'd get partway through the next shift and then the dosimeters would die. So just make sure that you don't forget to charge your batteries, because that's no one likes to do it again. So don't forget. Don't forget to do your pre and post calibration of 114 dB at 1,000 hertz. Most dosimeters have the same requirement. One of the cool things about the SKC one is you turn on the calibrator and you put it over the microphone area of the dosimeter. It automatically recognizes that the decibel level as well as the frequency, and it automatically puts the dosimeter into calibration, which is super cool. So something to also remember is to make sure that your windscreen is secured and in place prior to sampling. Now, you cannot just grab any foam to use if you forgot your windscreen back at the office. Like this, the foam that comes on the dosimeters is what's called acoustically transparent. It's good of knocking down wind up to 10 to 12 miles an hour. And so if you're sampling in a windy area with no windscreen, you can expect your results to be significantly higher than they would otherwise. Same thing if you decided to just go in your Pelican case and cut out a piece of foam and stick it over your microphone. It's not acoustically transparent. It's blocking sound that would have otherwise traveled right through the microphone and into the mic. So again, it's just one of those things. Make sure you always have your microphone cover and that it's secured and in place prior to you letting it go out into the field. So as far as where you want to put your dosimeter, this picture of the gentleman on the right is an excellent area to put it. It's right on the top of his shoulder, right next to his ear. There is not any chance of him messing with it as it sits. Of course, you have to remember that in winter and cold months, that some guys will put warmer layers on. If that's the case, when I would always do it, I would have them put on all their clothing first. We can step outside. We could put it on the very outside layer of their clothes to make sure that it's not being artificially elevated, because the clothes rubbing on the microphone creates a lot of noise, and it's not representative of their noise exposure. And kind of like earlier, as we were talking about, like informing the worker, talking to them, like talk about the purpose, like tell them what you're trying to do, how they can help you, how the dosimeter works, what will screw the dosimeter up, what won't. And typically what I found is the majority of people are willing to help you get a good measurement. Sure, there's bad apples out there that are going to try to mess with your stuff regardless of what you do with them. But for the most part, is if you can collaborate and work with the people that you're sampling to get a good sample, they're most likely willing to help you and not mess with your sample. And always the last bit, periodically check the placement, make sure it's where it's at, make sure the clips haven't come undone and it's flopping upside down, make sure they haven't put a coat over it, a vest over it, whatever it might have been, or if they, maybe they took it completely off altogether. Like that's why in industrial hygiene, we have to go out and watch people, check on them, make sure they're doing good, make sure the sample's doing good, and make sure it's where it's supposed to be. And again, helping people understand why we are taking these noise measurements is a huge part to helping those measurements be successful. So some additional considerations is, obviously there's people out there and employees that are not the greatest to work with. I think I could safely say we probably had most people that we sampled take off the dosimeter. Some of the ones I've heard that they're trying to help, so that they take the dosimeter off and they put it in their inch compartment. They put it somewhere really loud so they can get some additional funding for the, the noise project that we're trying to do. Like they're just trying to, quote, help, but in reality, all they're doing is making more work for them and for you, because you got to come right back out and do that sampling event again. And obviously at the very end, the sabotage of the measurements. Luckily, this hasn't happened too many times. We have had a couple times where people purposely are yelling into the dosimeter to give it false readings. They're purposely putting it places that are super loud to make it look like their job is a lot louder than it is. They're not always out there, but just watch out for them, because if I told you that it would never happen, I would definitely not be telling the truth, because there's a really good chance that people will want to mess with them. So again, just remember that wind interference that at above 10 or 12 miles an hour, it's going to start interfering with the measurement of the device. So if it's an absolute hurricane outside, it's probably not the best day to sample for noise if you don't absolutely have to. And again, not observing the worker during the monitoring schedule, that's kind of goes without saying. We understand the risks and issues that can happen throughout the day with our samples. So as far as real-time data backup, aka manual note taking, it's the OG way to make sure that your data is still good, even if your dosimeter dies, it gets lost, whatever else, partway through the shift. So whenever we would do noise monitoring in the big huge haul truck shops, I would draw the shop. I would draw where excuse me, where the trucks were. I would draw where the speakers were. I'd draw things and be able to better understand and communicate those risks back to the people because I documented that throughout the day. Now, one of the things that I would do, because our dosimeters at the time had a tendency to get their microphones ripped off, is every time that I would go and check on somebody, I would write down the time weighted average, the sound level at that time, what the dose was at that time. I would note down as much information as I could, just in case that sample was compromised or destroyed by the end of the day, or by the next time that I came back and checked on it. So these type of notes are invaluable when it comes to either rescuing data or by interpreting data after you could take it back to your office and download. It makes it so nice to be able to take your picture that you drew, maybe recreate that in Excel or in PowerPoint, and help people understand where the noise exposures are coming from. Whatever that looks like, taking notes is a great option. So some additional documentation that you can do is our dosimeter, as well as other dosimeters that you can connect to Bluetooth. Being able to connect wirelessly to that dosimeter, see what it's doing real time, take a screenshot, drop that screenshot onto your note-taking apparatus. The one that I use is called GoodNotes. It makes it really easy to draw, to insert pictures, to export as PDFs. Whatever type of note-taking that you use, being able to connect wirelessly to it can make your life a whole lot easier. And additionally, sometimes you go and check on people in the field and they are places that you cannot reach. Maybe they're in a lift, maybe they're in the back of a haul truck, maybe they're doing a job that they can't stop. If you can connect wirelessly to them through your phone or through a tablet, you can see real time what their noise level is. You can see what their dose is, what their what the time weighted average is at that point. Like you can key in and see what they're doing without stopping them from doing their job, which is pretty cool. So as far as best practicing for monitoring during lunches, I'm not taking a ton of time on this. Every company does it a little bit different. What it comes down to is it depends if the potential for noise exposure is going to happen during lunch or if it's not. For example, this picture on the right, this guy's in his construction site. There's probably jobs going on all around him. If he's still being exposed to noise during lunch, personally, I would keep his dosimeter on. When I was working at Hill Air Force Base during lunch, these people would take all of their tieback off. They'd leave all of their PPE in the booths. They would then go walk out to a clean lunchroom where it was quiet. And if for something like that, we would just pause the dosimeter during the lunch hour. Or as I'll show you with some software, you can just exclude the readings that were taken during lunch hour if that makes it easier. So long story short, it's very company dependent. It's very sound dependent. It depends on what you want to do. So make informed decisions and understand why you're making that decision to begin with. So quickly talking about the difference between the noise reduction rating of earplugs and the personal attenuation rating of plugs. Basically, the NRR is a laboratory derived number based on everything being perfect, what that earplug or ear muff is going to give you for protection. I got to experience this firsthand. When I was first in IH, we traveled back to one of the 3M laboratories, and I was able to do some of this NRR measurements. That there was a guy in a lab coat came out, squished down the earplugs, put them in my ear, made sure they were perfect, and then we would take sound measurements. So that's, I always joke with guys that I'm not going to come around and put your earplugs in, and so you can't use the full NRR in your space. It doesn't make any sense. So the difference being with the personal attenuation rating, pictured here is a 3M ear fit. It basically allows you to fit test the earplug for your ear, just like we do fit tests of masks for our face, for respirators. You're doing the same thing for specific earplugs for the individual's ears. So this is a great option to do. It's commonly referred to as a best practice. I love doing this. When I worked at 3M, I tested hundreds or maybe even thousands of people with this device, and it's awesome being able to see just how little protection some guys would get that you'd think otherwise. Meaning, we'd have a gentleman come in, we do an ear fit test on him, and the NRR was rated at 33, and he'd get like 35. Like, awesome, that's really cool. The next guy that comes in, big burly dude comes in, he's getting like 5 decibels of protection with the same plug. And it's because his ear canal was much smaller, it was tapered a different way. That particular earplug did not work well for him, even though it worked well for the other gentleman. So being able to use some type of fit testing like this really allows you to use the noise data that you've gathered in the field, at the same time being able to understand where those employees are being exposed and what earplugs are going to be very best for them, especially when the environments are louder than what you want. So the limitations of NRR, we've kind of talked about it. The common rule as far as derating goes is you're taking the NRR of that plug or muff, you're minusing 7, and you're going to divide that by 2. Now, I understand there are a number of other ways to derate, even within with OSHA, there's a number of ways. NOSH has a different way. The Canadians have a different way. I'm not going to go into that right now, but just understand from an NRR point of view that you cannot take the NRR at face value. There has to be some type of derating, and whatever choice, whatever method you choose to use, that's up to you. So quickly, before we jump into everything else, the dual hearing protection, what is actually happening? So if you remember me talking about the blast booth at Hill Air Force Base with the F-16, when we first got noise dosimetry back, we went and met with the engineers that were over the project to help reduce the noise. And they're like, I don't know why we're even having this conversation. They're wearing a muff that is 29 decibels of protection. They have a plug that's 33. Like, they already have 62 decibels of protection. So why are we even doing this project? So at that point, it was fun to help them understand that you cannot just simply add the decibel rating on NRR to get an end result. In short, you're taking whatever the maximum NRR correct value is of the muff and the plug that you're using, and you're getting a maximum of 5 additional decibels of protection. Not doubling it, you are getting just 5 extra. So we kind of talked about this, leveraging the mobile app for connectivities. This is a screenshot of what it looks like real time when you're looking at your app and when you're connected to the dosimeter. So again, screenshot it, put it in your notes, make it super easy, especially if you have bad handwriting. So let's see. Awesome. I am going to shift gears real quick. I'm going to change screens and we're going to hop into the software and kind of go through these type of things in the next 10 to 15 minutes. Hopefully we have enough time for some questions at the end, but that's the plan from there. Okay. Here we are. So when you open up the SKC software, there's a number of tabs across the top. We have a setup tab, a schedule tab, and a history tab. When you have a dosimeter, which I have right now on the dock, the setup tab populates, and this is what you can see. The nice thing about the setup tab is if you notice in the area down at the bottom, where it allows you to choose what type of measurements you want to make. You select hearing conservation from OSHA, the OSHA PEL, or the ACJH. These are pre-populated. You cannot change these parameters. So you accidentally can't have a 90 decibel threshold for your hearing conservation. At the same time, you can't accidentally change the exchange rate on OSHA to 3. These are set, that these 3 are the ones that will come up by themselves. This fourth tab over here allows you to add another one, or you can make your own. In this page right here, you have a couple of other options. This part up here, this is the information that allows you to show what readings you want to see on your dosimeter while it's being used. So in the field, these are the measurements. The ones with the check marks are the ones that I'm looking at. From as we go down the list, logging our data. Are we logging it every 1 second? Are we logging it every 60 seconds? Do we want to C or Z weighting? And do we want to lock it? The one thing that I want to point to on this page, and we'll talk to a little bit in a second, is this auto record feature right here. Now, what this is I don't know how many times I've been sampling in the field. I get my noise dosimeters back to the computer, download them, and I see partway through the day, there is this crazy loud peak of something that happened during that day that happened when I wasn't there. And so I go back to the guy that I was sampling and say, hey, what happened at 2:05? Like what happened? And like how many times the guys were like, I don't know. I was just working. I have no idea. So what the auto record allows you to do is you can set it at a threshold of whatever decibel you want. If it meets or exceeds that threshold, it will record a 10-second blurb of whatever that sound was. Was that a bearing that they were working on? Was it a truck that started up? Was it the radio that went off? Were they jamming to some super loud music? It gives you a short 10-second sound clip that you can play on your computer, and you can see exactly what that noise was that previously we would never be able to identify. So I absolutely love that feature. We'll talk a little bit more about that when we get later on, but that's a big one for me. I absolutely love that. So when we're talking about scheduling up here, you can schedule when you want to start and when you want to stop. You don't have to use this. When I was underground in the mines, we'd always have ours turn on at a certain time, and we'd always have them turn off at a certain time. It made sense. It was easy for us. That's the way that we did it. This is what allows you to do the same kind of a thing. So in our history screen, on the top up here, you can see all of the results you've ever taken that are downloaded into the software. These are the ones that I've kept, the ones that I think they're interesting to look at. Down here in our summary, this gives us the summary. I'm going to change it over to the one that we were talking about, the guy that was just on the very cusp of hearing conservation. So this is his. So we have our summary of the results for the 3 different dosimeters that we're recording at the same time. We have our information down here of our pre and post calibration, the times. If we go into our logs, this allows us to go in and change and look at different things. So this particular graph, you can see throughout the day, this was his shift. He worked for 9 hours and 49 minutes, almost 10 hours. And during that time, he had a decently loud day. Now, looking at this graph, there's a couple of things that I want to point out. If you look down here on the bottom right, you'll see a number of red little marks that are inside of this green line. So inside of our noise dosimeter, we have an accelerometer, so we know when the dosimeter is moving and when it is stationary. So we can see during these times, especially this time, this dosimeter was not moving. So either he was taking a nap or he took that dosimeter off and put it somewhere that was decently quiet. So maybe he took it off, put it on his desk, and then went outside to do another task that was loud. Maybe who knows? Maybe he was having some food. I don't know. Whatever it is, being able to see when that dosimeter was moving and when it was not is a huge help, especially when we're trying to figure out what's going on. So as far as this tab over here, this little chevron that you can click down, you can click any number of things to display on the graph. Personally, for me, the ones that I like the best are your LEQ and your Lmax. And let me tell you why. If we are looking at these, we can see what our noise level was throughout the day based on a normal exchange rate as well as no threshold. If you change this over to L average, as far as the graph goes, it's similar, but at the same time, we have all these areas that were below our threshold. And so it makes our graphs very busy and kind of confusing. And so for that reason, using the LEQ and the LMAX is what I like to display. And the reason is our LEQ is our average over the entire shift. Every minute it plots what the average noise was for that time. Same thing with LMAX. It's plotting the highest noise that happened during that 1 minute log, and it's plotting it. So as we look across our graph, we can see 1, 2, 3, 4, 5, 6 events that are over 100 dB that are not showing up in our LEQ. So if I turn off the LMAX, we see that we're not coming above that 100 dB mark. But the nice thing is about having that LMAX is it lets us see where those loud events occurred during that period. And if I want to kind of zoom in and look at that particular spot a little bit more, this little zoom feature over here allows you to zoom into a field and kind of blow that up so you can see exactly down to the minute when that was and how high it was. So it's a great feature to be able to help people or to find out what happened during that time. If I had set a threshold on my dosimeter that any noise over 100 decibels, it would record a noise. We'd see that for this one right here, it would record a noise because right here, let me get out of there, wrong one. There we go. So for here, we're at 102.7. Right here, we are at 99, so just under the threshold. So anyway, it allows you to dive in and look a little bit closer at the data. I'm gonna get back out of here. And so earlier we talked about this guy, based on our summary, is right on the threshold of hearing conservation. Let's pretend that during that time that this area right here, he actually took his dosimeter off because it was super duper loud and he didn't want to add any additional noise to his exposure. So what you can do, which is kind of fun, is this little button over here allows you to look at and change the noise levels as far as a what if kind of a scenario. So if we were to highlight this and we were to make this zone, if we were to increase that noise level by about, say, 15 decibels, what would that look like? So if we can go back to our summary page and we can see, based on that short period of time, if we were to increase that, obviously he's definitely above 87 and now he's definitely above his dose. So being able to see, we can add noise into the equation, but at the same time, let me get rid of this zone, is during his shift, let's say this job right here. This was done by an old piece of equipment. It was done by something that was super duper loud. We know that it's loud. We've been looking for a reason to get a new piece of equipment. Let's just pretend that we can take that particular job and we can offset that by, let's say that we're going to knock it down by 6 decibels, which we've learned is a lot of energy and a lot of pressure. So let's knock it down by -6 dB. So just by doing that, replacing that with a new piece of equipment or by doing something else, we were able to reduce that particular job by 6 decibels. You can go back to our summary and see, okay, like if we were to replace that noisy piece of equipment with something that was quieter, maybe something that was gas powered to something that was electric, for example, we would clearly be well below that legal range of 87 and very low below the range of 66. And so the nice thing is too, is you don't lose the original data. The original data is down here in the bottom, and this graph up here or this table up here is what happened based on the what if analysis that we had created. And so by being able to play what if on a lot of different scenarios, you can see what different equipment might do to the noise. We can see what it might do for employee hearing hearing conservation, whatever that might be. So in the last minute before I hop off of this, I wanted to show you this picture or this graph right here. This gentleman right here he had a dose of 1%. And what's really fun and really interesting is if you look, this was set up from the ACGIH with a threshold of 80 decibels. So if you look across the time, there is 1, 2, 3, 4 times across the entire day that it just barely blipped above 80. And so all of this information down here that was below 80 dB, it was not included in the final readings of the dose because it didn't meet that threshold. This is the first time I've really seen an excellent example of threshold, and this is dead on of 80 dB, and it turned out really, really cool. It's a really fun learning opportunity, and yeah. So with that being said, let me change my screen back, and Hunter, if there's any questions, this is our time.
Thank you, Dusty. Doesn't look like any questions have popped in the question box here. Looks like you went over everything pretty thoroughly for everyone. If anybody has any questions, right now would be the best time to throw those in. Give it another 30 seconds to a minute.
Okay, and just so everybody knows, that QR code on the screen, that is my contact card. If you scan that with your phone, it'll bring up my contact. I have my name, my number, my email. If there's any questions you have, I figured that was the easiest way rather than have to have you manually put it into your phone. So hope that helps.
Yeah, that's awesome. Thank you, Dusty. Those QR codes are so nice these days. All right, no questions have popped in. So with that, Dusty, thank you for enlightening us today with your presentation. Any specific questions in regards to equipment, I highly recommend viewing our training center on our website. We have training videos demonstrating equipment operation. We have past webinars and blog posts for educational content on industry standards. Feel free to give us a call at 866-RENT-EHS or 866-736-8347. You can also reach us by email at rentsconfirmation@raycorents.com. We are always open to new topics for future webinars. If you have a subject you'd like to see covered, we would love to hear your feedback. Please fill out the post-webinar survey or send us an email. Thanks everyone for attending our webinar. Have a great rest of your day. Thanks again, Dusty.
Thank you.